I'm going to start recording. She already got all that part. I don't know why I stopped recording, but it's recording now. Maybe I'm sure it was user error on my part. Okay, we're recording now. And she just left. Yes, her Wi-Fi might have gone out, but she had to leave too. So.
Hi, Abby. Love you.
Oh yeah.
Doug.
Oh.
Yes, we'll go through that chapter. I was going to say something else. Something you said made me think of it. I think. I don't know. I just lost it. There's something else I was going to say.
I love just seeing one of the people in your house standing in the back, like looking through VR. Like,
no, is he still? Oh, yeah.
Truthfully, is a great experience in addition to class.
Okay, what was I going to do? Hopefully you read Module 16. It'd be nice if you did. So Module 16 talks about oxidation reduction reactions. And they begin in the chapter talking to you something about oxidation numbers. And as you read about oxidation numbers, maybe something in your brain was saying, you sound like when you find out what the ions are and the charges to balance it and get the formula for something. And they are deceptively similar. They just represent something different, and their use for them is different, and they aren't always the same. And so what you'll find as you read the beginning of 16, it's not necessarily hard. It's almost more just like a puzzle. And then you're kind of like, well, why do I even care about these oxidation numbers? And then you find out a little bit later that you're learning about oxidation reduction reactions. And what happens in an oxidation reduction reaction, it's a mouthful, is that you'll have something that has a certain oxidation number, and that oxidation number will change. It'll either get higher or lower. And it has to do with exchange of electrons. And so something gets reduced and something gets oxidized. Probably the most obvious example of that is when you see something rust. So if you've heard something like that's getting oxidized, and that comes from an oxidation reduction reaction. That's where that terminology comes from. So anything that, like when you see rust, if you see copper when it kind of turns green and gets that patina, sometimes in jewelry making they use that as something beautiful. That is also an oxidation reduction. So sometimes it's destructive. Go ahead.
Like when you put fake jewelry on, it turns your finger green.
Yeah, I think that would also be the same. I don't know for sure if that is actually, I'd have to double check. No, it is. I'm almost certain it is, because that's like a tarnish, or like when silver tarnishes. Yes.
The whole copper thing was like my whole like presentation that we were supposed to write like 4 weeks ago.
Oh, awesome. Did you ever send that to me? I feel like I saw Caitlin's, but I don't feel like I saw yours, Emily. Did you send it to me? Or
did you read mine? It's kind of a hot mess.
I apologize. I am so sorry, guys. I've been like a little overwhelmed for some reason. This not in a bad way with quarantine. Like everybody talks about their lives being slower and they're bored. That's not the case for me. So I feel like we're just like.
That's not the case for anyone who has like more than 2 kids.
Yes, life has not really changed other than like there's not a break, which actually I don't mind. I mean, there isn't a lot in my life normally. I'm usually home all the time anyway, but grocery shopping is my break right now, which actually is kind of nice. I do like shopping with my kids, but it's particularly crazy.
Yeah.
Anyway, that aside, it's not because I'm not interested in your paper, Caitlin. It probably fell off my radar, but I will get it read. And I look forward to reading it, so don't.
You'll probably laugh a lot.
Well,
no, we're not
going to be like it's going to be like a.
But that's awesome that you did it on copper, so that kind of comes full circle for you in this unit. So
I did think about a chemical reaction so that I could explain it easier.
Say that again.
Simple concepts.
What a queen.
That's good. It is good. Oxidation reduction is not always destructive. It's not always something where it's rust or tarnish. Batteries also work, which was new to me. I like learned something new in this unit because I didn't know a ton about that. So anyway, you will also see how oxidation reduction reactions can produce charge and electron travel so that you can get energy from that battery charge. So anyway, that first section is you have to figure out those oxidation numbers. That's so that you can then evaluate reactions where you can look and say, what was the oxidation number as a reactant, and then what is the oxidation number as a product, and does it change? And then which is the one being oxidized and which is the one being reduced? And we'll talk about that terminology. So that's kind of the big picture as you look at these oxidation numbers. I even had to look it up. I'm like, what's the difference between oxidation and ionization, I guess, number? That's maybe the right way to say it. And there isn't, there's just rules. There's just rules. And I just heard you, and I'm debating about, I was reading that, I'm probably going to let you use those rules on the test because it feels like it's not useful to you in everyday life to memorize necessarily, but if you can at least evaluate that, apply it to the reaction. That's the part that requiring like some brain knowledge. So page 562, they give you 6 rules to determine oxidation number. And so as you get something, you'll just go through those rules and kind of see, well, let's just read through them. So the first one says, when a substance has only one type of atom in it, and they give you some examples. So F2O3, Ca2+, Mg, magnesium. So it doesn't matter what it's charged, but if there's only one type of atom in it, the oxidation number for that atom is equal to the charge of the substance divided by the number of atoms present. So if you look at those, well, F2, fluorine, has no charge on it, right? So the charge is 0. So 0 divided by the number of atoms present, which is 2, is 0, right? 0 divided by 2 is just 0. So its ionization number, 0. That's pretty easy. Same with that oxygen. It has no charge, so 0 divided by 3 is 0. It's still going to be 0. That calcium 2+, it has a charge of 2, but there's only one atom. So 2 divided by 0, I think is actually even undefined, but for our purposes, it's just, it's 0. It doesn't have an oxidation number. And that magnesium, similarly, it has no charge. It only has one atom. It's just 0. Does that make sense, that first rule, just generally speaking?
What's the first rule?
Did your brain go into a black hole?
Yeah.
I got lost at the point that you were just talking numbers.
Okay.
I'm gonna just be honest, I did not read the book this week, and like I don't.
Okay, well, if you didn't read it, that would be a good reason to pay attention. So it'll make your work less hard this.
Yeah.
So if you have your book, I would encourage you to open to page 562. It will probably be much easier if you're looking at it and hearing it.
Okay.
I don't know. That's me. That might not be if you're better at learning by listening, then that might not be true. It helps me to see it and hear it.
It helps me too.
So they're just giving these rules. So you're going to get they'll give you a question that says, what's the oxidation number of H2? Or what's the oxidation number of CaOH2? And you're going to have some strategy to figure out the oxidation number. And you're using these rules to figure it out. And again, the bigger picture is that once you know the oxidation numbers, you can look at a reaction to find out if it's an oxidation reduction reaction or if it's something else based on how those oxidation numbers change. So you have to know what they are to know if they change, right? And that's the bigger picture. So now it's like we're moving in closer and we're actually just trying to figure out how do we find those. So that first rule just says, this feels like when you're reading like rules for doing your taxes or something, like if this line is more than this, but you made this much money in that, it feels kind of like that, which you guys probably haven't done your taxes too much or not.
I just did my taxes literally like last week and I wanted to cry.
I hate to tell you, they only get more complicated as you get older, but.
Dude, my dad was independent. They're like, you don't have any independence. You can claim what you gave to church.
Well, yeah, you can. I don't know how that works for you now since Trump is president. It's changed. It's actually simplified quite a bit from.
I don't know, but Dad goes, put down the money you gave your sister. And I go, okay.
Your sister. You can. That's true.
One second.
So that first rule is just simply saying when a substance has only one atom, only one kind of atom, so just essentially an element, only one kind of element in it, the oxidation for that number is going to be equal to the charge on it divided by the number of atoms present. So they give some examples of numbers there, and I was just trying to explain why those are all 0. Because now this is not saying just because if it has one type of atom that it always is 0. It's not saying that. Although if there's no charge and it's one element there, it's always going to have an oxidation number of 0. So you could kind of cement that in your head that if it's just an elemental substance with no charge, its oxidation number is going to be 0. Because it's always going to have no charge, which means no charge, 0. Divided by, no matter what's present, you can't divide 0 by something and then get a number. So you could lock that into your head from this rule that if I just have some element, Fe2, Cl2, O2, Mg, any element on the chart by itself with no charge, automatically its oxidation number is 0. Let me look for it. But like if I had, I'm trying to find an example here of one. We'll wait till we have an example. I'm trying to think, like if you had,
Are there any in the practice problems or the OIOs?
practicing getting these oxidation numbers?
Yeah.
Oh,
is
yeah.
there an example in the OIOs? We can
Yeah,
do that.
we'll go through some of them here. I just want to read all the rules and I'll show it to you in practice. I think it makes more sense in practice. Hey, Angeline. Oh, hey, Angeline, your shorts are tucked into your skirt. Just pull it up. Come here. Let me fix it for you. You're like tucked into your shorts in the back. I'll fix it, sort of. Well, they're still kind of tucked in there, but oh well. Okay, and then if you remember on your periodic table, you had that group 1A and 2A. They're all the ones way over on the left there that with hydrogen up in the corner. The first column is 1A, second column is 2A. So it tells us group 1A metals always have oxidation numbers of +1 in molecules that contain more than one type of atom. So if I have a group 1A and it's mixed with something else, its charge is going to be +1. And that's to differentiate when it's by itself, which would then you'd go back to rule number 1. This sounds like some silly meme. Yes.
No Spanish baby.
And then second one is similar. It says group 2A metals always have oxidation numbers of +2 when they're in molecules that contain more than one type of atom. So fairly simple. Number 4 says fluorine always has a -1 oxidation number in molecules that contain more than one type of atom. So if fluorine's by itself, we're going to refer back to number 1. But when fluorine is mixed with something else, it's always going to be -1. It just feels so random, like fluorine is -1. All right, so you just accept it. The rules aren't actually that complicated, it's just trying to keep them straight. It says, and then it says, what's nice about these 4 rules is that they're always true. So those first 4 rules, always true. The next couple of rules, there are some exceptions, but we're not going to have to really worry about the exceptions. They're just letting you know that just for your knowledge base. So the next 2 usually apply, or the next 3 usually apply. I'm sorry, there's 7 rules, not 6. 7 isn't really a rule. 7 isn't really a rule. It's like if all else fails, do this. Number 5 just says when grouped with just one other atom that happens to be a metal, this is the one is a little trickier, hydrogen has an oxidation number of -1. So, stepping on my fingers. So, and you'll see, this will make more sense when you realize when you're finding the oxidation numbers for a formula, they all should add up to 0. And so, so when hydrogen is grouped with something that's a metal, so all that stuff on the left, right? Then it has an oxidation number of -1. In all other cases, when it's grouped with other atoms, it has an oxidation number of +1. So again, just tuck these away. We'll work some examples. And then number 6 says, oxygen has an oxidation number of -2 in molecules that contain more than one type of atom. Again, that more than one type of atom is just because if oxygen's by itself, you go by rule number 1. But when oxygen's mixed with something, it automatically has an oxidation number of -2. So what you're going to be doing is you'll get a formula. You're kind of referring to these rules to say, what is something I know based on things they've told me? And then how can I deduce what the rest are? And then the very last rule says, if all else fails, I have no other, I can't go by these other rules, I don't have any other information, assume that the atom's oxidation number is the same as what it would take in an ionic compound. So remember when we could look and say, in that number 7 column, it's -1 because of the valence electrons. So kind of going back to what we were doing. You know, I wanted to say, when I said we're not having a cumulative exam, we're not, but when you think about it, we've used a lot of the things we've built on.
Yeah.
You know, things do build. Now there's some specific stuff, you know, that we did with solutions maybe, but even that, you still have used molarity, and you've used not molality as much. That was pretty specific to those freezing point depression and boiling point elevation, but you still use molarity. You know, we haven't always used gases, but some of that has carried along. Now, what I will say is if I give you a question that assumes you know something from before, you know, I'm not gonna pepper it with that, but there might be something here and there. Sorry, stuff that I would, like stoichiometry. Like stoichiometry is part of what we've been using all along. So anyway, that was part of my reasoning, that some of that has built, so you're still using it all along. Okay, sorry, I completely went in a different direction. Mainly because this rule goes back to something that you used before. So let me read that again. If all else fails, assume that the atom's oxidation number is the same as what it would take on in an ionic compound. The atoms that are most likely to follow this rule are in groups 3, 6, and 7A. So if you don't have your, I don't have mine over here, your periodic table, you could use the one in the book, which is on page 52. Okay, so given all that, let's work a couple of on your own problems just to take a look at this so that maybe we can see it less in theory and more in real life, which would be probably much more helpful. Just give me one.
We're in module 16.
We are in module 16, yes. It's good to know where we're at.
I was writing on the module 15 notes part.
Okay, just label it and say.
Like a dingus.
Nothing happened, I'm just sharing my screen.
That's it. You cannot eat the notebook.
You can see it. Okay, so let's see. So we'll start out easy. Example 16.2. This is on page 563. They ask us, what's the oxidation? Please don't do that honey, right now.
Black.
Okay, you want me to use black? I'll use black. Okay, so what is the oxidation number of each atom in the following molecule? So we start out easy. They give us hydrogen and say, what is the oxidation number? Please don't start touching things. Can you just, it's just distracting them. Okay, you're super cute. Where's your shirt? Free spirit. That is true. So it says, according to rule 1, hydrogen's oxidation number is 0, or is 0 divided by 2, which is 0. So there's no charge. That's where I get the 0. Divided by 2. There's 2 atoms present. 0 divided by 2, though, is 0. So its oxidation number is simply 0. That's the simplest one, right? But then they ask us.
Wait, are you doing an on your own question?
Yeah, well, no, these aren't on your own. This is just the examples in the book, so you can work along with
Okay.
Don't start coming up the camera, so, although I'm not even using that camera right now. So I'm at the bottom of page 563. Evangeline, can you stop? Like this finger from heaven coming out of nowhere. So problem B says we've got calcium hydroxide. In this compound, we can apply our rules to every atom. So we look at CaOH2, write this down, and we just start looking for rules. Now here's what's maybe a little confusing. We used to consider this hydroxide, this polyatomic ion together, and we're used to considering that together. We're like, if we know the charge on calcium is +2, right?
You're telling me we finally get to use them separate?
Yeah, so that,
I've been waiting my whole life for this.
I know. So we would say that was +2, and then there's 2 of these, so we would know that was -1, or that polyatomic ion had a charge of -1, each one of those. So you got to kind of not forget that, because that's still important. That is like the charges on those ions when they dissolve in water, but we're doing something different here with oxidation number. So that it's different, and we are considering everything separately. We actually are considering the oxidation number of each of those elements involved. And so we look and say, they gave us that rule that said group 1A metals, or sorry, 2A, calcium's in 2A. So if you look on your periodic table, you find calcium, it's in that second column, which is 2A. And we have our rule number 3 that says those group 2A metals, as long as they're with something else, have an oxidation number of +2. So we can just say calcium, here, let me write it on the bottom. Maybe that will sort of do it. Yeah, we'll say oxidation numbers. We'll put those on the bottom. What do you need? She just came in and said, can we not watch something? And she was trying to say educational, because I asked Delia to put on something educational, so they went and just watch Lab Rats. So
Evangeline, you win.
Can we please be done with the educational? Yeah, you can, but I don't want you to watch Lab Rats, so you can't tell Delia if it was okay to watch. Unless someone else is interested in it. Is someone else interested in it? She could just go pick up a book. Okay, so we does that make sense? That charge on calcium, that oxidation, not charge, I'm sorry, that oxidation number. Let me pause for 1 second. I kind of skipped ahead to here's what oxidation numbers are. Oxidation numbers are something completely theoretical. So these elements, they will never have this charge. But if you remember how when things would bind, like something is more electronegative, so it tends to pull those electrons closer to itself, so it's going to hold on to all the electrons more. This is in theory if that element or atom could take all the electrons, what would its charge be? And that's where the oxidation number comes from. But again, it's purely theoretical because it never will have all the electrons. It just tugs on them more. So that's where the oxidation, I'm sorry, I kind of like just skipped right over that. But when you read the chapter, you'll see that. So I just wanted to back up and say that. Okay, so calcium is +2. That's just one of the rules that's listed. That's where we get that. And then rule number 6 tells us about oxygen. So we're just kind of looking in there and saying, what are, like, I learned something about oxygen. I learned something about hydrogen and calcium.
Oh, you mean oxygen and hydrogen are separate?
Yes, that's what I was doing. This is different than when you would consider the ionic charges to get the formula. You got to really get that in your brain. It is a different process. Each one of those elements is going to have an oxidation number, and they should all add up to 0.
Okay.
No, I don't want you to start downloading those because you have stuff on there.
Dash art.
I don't care. Then you got to find something.
You don't just get to do that. Stop it. Stop it.
It's for a different purpose. So it's, yeah, that might be the part that's confusing. So you just have to kind of say that in your brain so you get that concept down. So rule number 6 tells us that oxygen has an oxidation number of -2 in molecules that contain more than one atom. This contains more than one atom. So automatically oxygen is going to be -2.
Gotcha.
And then they tell us about hydrogen that when grouped with just one other atom that happens to be a metal, hydrogen has an oxidation number -1, and in all other cases, when grouped with other atoms, it has an oxidation number of +1.
These are in the rules.
What's that?
All that's in the rules.
Yes. And like I said, I'm willing for you to have the rules. I don't really care about you memorizing, I care more about you applying them. So for the test, maybe it can be that you write them out on a card and then you have that card with you. So this is probably the one time that I let you write something out on a card. So you have to write the rules out instead of using your book, but then you can have those with you. So I'm gonna look at something here. So we have hydrogen, and as I evaluate that, I think the confusing part is you could say hydrogen's grouped with oxygen, which is a non-metal, and it kind of looks like, oh, it's also grouped with calcium, but I think we're just going with the fact that it's grouped with oxygen right there in that polyatomic ion, and so that's why it's +1, and we have 2 of them. And let me see something here, let me make sure. So let's just put +1 there. Did that make sense what I just said? Probably not. In that rule, it was saying that when hydrogen is bonded or what is the word they use? Happens to, when it's grouped with a metal, which oxygen is not a metal. When it's grouped with a metal, its charge is -1, but when it's grouped with anything else, it's +1. And so that's why I got +1. So now everything has a charge. So what I want to do is just double check that everything adds up to 0. So I'm going to say I have +2 plus, now I'm going to say 2, because there's 2 of them, 2 times -2 for that oxygen, plus 2 for the hydrogen times 1. I'm just putting those pluses in there just so you can see like each piece of it. So then I have 2 plus 0. Wait, so no, I'm wrong. What did I do wrong here? Oh, no, that's -4. Plus -4, I didn't multiply. Plus 2. Okay, it is right, sorry.
So negative times negative is a positive.
So I have, look, let me do that over again. I was just doubting my multiplication. Okay, so I have 2, right? That's just a +2. I put all the pluses and negatives so you could see them from what I was getting from here. So that +2 just came from that calcium. That -2 came from the oxygen, and that +1 came from the hydrogen. And because there's 2 of those molecules, I multiplied each one of those times 2. Does that make sense?
Yeah.
Okay. This is still recording. Okay, so now I'm just, yes, reducing all my positive and negative. So I have 2. I just took that +2. I'm just writing 2 plus 2 times -2 is actually -4, right? So I'm going to actually just erase that positive sign, right? 2 times -2 is -4. So I have 2 minus 4 plus this here, just 2 times. Yeah, don't be, you know what? I can see how I wrote that as confusing. I meant that as 2 times +1, and it looks like 2 plus 1. That's not what I meant. I apologize if that was confusing. So now I have 4 minus 4, and yes, that equals 0. So my total charge is 0. So that's all there is to that. It's just not really particularly hard. It's just getting used to using those rules. So let's look at another one together. If we flip the page, and really, to tell you the truth, this is the most complicated part of this chapter. It's just finding those oxidation numbers, and then they'll give you a reaction, and you're going to find all the oxidation numbers. And maybe the next leap is just trying to figure out which is the one that's oxidized and which is the one that's reduced. And we'll talk about that as well. And I don't necessarily think it's hard. It's just like maybe the next piece. And then they just show you how oxidation and reduction are used in life, like in batteries and in things rusting, application of those. So it really actually isn't a hard chapter. So if you can just kind of take a deep breath. I know this is new, so it feels a little like, what exactly are you doing here? But I think once you work with it, you won't feel quite as overwhelmed by it. It's really not terribly hard. And there isn't a whole lot of hard stuff in this chapter. So as you master this, you're kind of mastering the hardest part of it. And so the next one, letter C, they give us F2CO. And so right away, we can look and say, what are some things we know about? We actually have a rule about fluorine there. And we have a rule about oxygen. So we can start grabbing those rules that we know. So fluorine was in that rule number 4, that it's always -1 when there's more than one type of atom. There's more than one type of atom, so great. I've got a -1 charge. Already got that figured out. And then we don't have a rule for carbon, but we do have a rule for oxygen. So we're going to be able to find out carbon by process of elimination here. If we know the charges have to be 0 and we know 2 of them, we'll be able to figure out that last one. So we know that oxygen from rule number, what rule is it? It's always -2. So it's just rule number 6. It always has an oxidation of -2 as long as it's with another atom. It's with other atoms, so great. It applies, so it's -2. So overall, fluorine here, since there's 2 of them, is going to be -2 plus that -2 from oxygen. I get -4. So what do you think the charge needs to be for carbon? Vote on a number here for me. Oh, Emily's outside. That was a good idea. Did you guys?
The puppy was barking at everything, and Michael wanted to play outside. So now we're outside.
Okay. So I was just looking and saying, if fluorine has an overall oxidation of -2, it's -1, but there's 2 of them there. So overall, it's -2, and oxygen is -2. So overall, I have -4. What would that make carbon be? I see Katelyn saying 4. Does anybody agree with her? Abby, Houston, Emily, do you guys agree with 4? Smart to go with your sister there, Abby. Delaney Wagar, stop distracting her. I don't
pay attention.
I do not believe you. I know she's sitting right next to you, and I know a direction.
She's actually not.
Mm.
She's not. She's going to the store.
All right. Okay, so
She's not directly next to me. She's just 6 feet away.
So yes, by process of elimination, not process of elimination, by just adding what's there and saying, what do I need to add to that to get to 0? If I have -4, yes, I need to add 4 to get to 0. There's only one thing left. So my final answer is that fluorine has an oxidation number of -1. It's not -2. The charge on fluorine, its oxidation number is negative. So that's an important thing. The actual oxidation number for fluorine is -1. The oxidation number for carbon, I'm just using my shorthand, carbon oxidation number is going to be +4, and the oxygen oxidation number is -2. So if I were then looking at a reaction, that would be what I wrote above each one of those and then look to see if it changed. So just keep that in mind. Fluorine is not going to be -2. It's just that when I try to find out the overall charge, there are 2 of them. So it's -1 plus -1 is -2. So your final answer for what is the oxidation number, though, is that it's -1. Does that make sense?
Mm-hmm.
Okay, Abby, you're muted, but I think you're saying, are you talking to me and saying you think so? Or are you talking to someone else?
Sorry, my dad asked me a question.
No, it's perfectly fine. I'm not trying to call you out. I just couldn't hear what you were saying, so I didn't know if you were being saying I think it makes sense. That's perfectly fine. Okay, so that's that one. Let's look at D, NaSO4 negative. So now we've got something with charge on it, so it's a little more tricky. NaSO4 negative. So we see from rule number 2 that 1A and 2A columns, sodium's in that 1A column, so we know that it's going to be a +1. So that's easy. Rule 6 says the oxygen has to have a -2 oxidation number. Okay, great. And there's 4 of them. So we're going to have -2, but there's 4. So it's actually going to be -8 out there. And then, let's see.
For oxygen?
Right, that comes from a rule. That's just from rule number 6. Oxygen has an oxidation number of -2 in molecules that contain more than one type of atom. That's one of those rules that falls into the usually true, but you can go with that. You don't have to worry about exceptions in this class. That would be beyond this class. So you can go with that rule as being true for our purposes for now. And then once again, like it says, we have no rule for S, but we can figure out its oxidation number because the sum of all the oxidation numbers equals the charge of the molecule, which is -1 in this case, right? It's not 0. It does have a charge. So I have +1, -8 equals -7, right? So what does S need to be so that I still end up with a charge of -1? Does anybody agree with Katelyn? Abby and Emily, do you agree? Would you?
We want to end up with a charge of -1.
Yeah.
Wait, why?
Because that's just the formula has a charge of -1 to begin with.
6.
Yeah, it would be 6. Yep. So it's going
Boom,
to be.
baby.
So yeah, so if I say -7, just to double check my work, yes, I end up
That
with
makes sense. I thought you were still trying to equal it out to 0.
Yeah, I figured you dismissed that. So yeah, so that's how that one works. Okay, so let's see. Let's go to E, which is C2H4. We don't have to do every single one, but actually let's do let's just since it seems to be making sense to you guys, let's just we'll skip to G, which is MgCO, that cobalt.
Is this the entire lesson, just doing these?
No, but it is the majority. That's what I was saying. I just want to make sure you get that. The next part just talks about actual oxidation reduction reactions, which we'll look at some of those. Check the time.
I would just like everyone to know that Dash has a stick bigger than his entire face and his mouth right now. And it's quite funny to watch because he can barely pick it up.
That's super cute. I love when puppies do that. And he's such a little puppy. Okay,
They
so
said he could double in size. He's cute.
he could double. I thought you said he was almost full size, so he could get bigger then, huh?
Oh, that's what the lady who sold us to him said, but the vet said that he could grow up to be 15 pounds.
That's so funny. Our dog is like 80, so that's 15
Which
pounds.
is still teeny, but right now he's 8 pounds. So it's about double.
Yeah, I mean, that is significant. I mean, he is only 8 pounds. Hey, Nation, are you still in the family room? Okay, thanks, Delia. Did you need to do something for school? Do you need to be doing something? Oh, because you don't have your computer? Okay. Okay. All right, thanks, hon. Oh, okay, so I'm just doing letter G. I skipped a few. It says in this compound, we know magnesium is +2 because it's in that group 2A. So you just, again, you start looking at things, what might I know something about? I don't know anything about, or actually I do know something about those. We'll get to that. But I know something about magnesium. That's a pretty easy one. It's in the 2A, so it's going to be +2. And then for the rest of them, those first 6 rules don't apply. So I'm going to have to go with 7, that rule 7 that said if in all else fails, you're just going to look at those ionization numbers. So if you remember that from number 7, or what the oxidation number is going to be the same as what it would take on in an ionic compound. So again, kind of what we did before. So we can look at cobalt and say, okay, it's, where's cobalt at? It's in that transition metals column. Wait, so what's
Mr. Dwegar,
yes?
what is the thing at the end of VR?
It's a 4. It's just a messy one here. Let me make that. My stylus was just being uncooperative. There we go. That's a little better, not much. I have to write so that I think you can get those gloves so you don't like touch the rest of the screen, but I feel like I'm always trying to write without like my hand resting on there, and I do find it affects my handwriting. So
I've always thought about that. Like, would it affect it if you had your hand on it?
I know. Well, yeah, it does. That is off from my hand. So yes, indeed it does. I wouldn't have thought about that, but I saw some of these styluses came with like a glove, like the sort of half glove that you wear. I'm sure you could like finagle something, just like cut the fingers off of a glove that is not a touchscreen glove or whatever.
For sure.
I just have not done that yet, but it's a good idea because then I could probably write a little bit better. So maybe I should think about doing that. Okay, so as it says, we're stuck with rule number 7. So we're going to apply this to the bromide or bromine for 2 reasons. Which, so first, it says that those rules are most likely to apply to things that are in columns. Whoops.
3, 6, 7, 8.
Yeah, thank you. And it is not in one of those columns. The cobalt is not. which makes sense, right? Because it's a transitional metal, so it didn't have a number that we could usually know unless they gave us more information. And so we're gonna find the bromine because it's in group 7A, which that last column before the noble gases, and so it's gonna have a -1 charge. And so that's why I end up doing that one first. So even though I'm going to rule number 7, if I look at cobalt, I don't have an immediately obvious answer for what that would take on, because normally they had to tell me like cobalt 3 or cobalt 4 or something, so I knew what its charge was. But bromine, because it's in that 7th column, it's got those valence electrons, it's very obvious it's -1. And so if it's -1, then I have an overall of -4. That magnesium is
So cobalt is 2.
Yes, very good. That is indeed true. And so that's what each of the, yes, thank you for, oops, the heck. So yeah, so magnesium is +2, cobalt is +2, bromine is actually, each one of those is -1. So that's what all of its oxidation numbers. So if that seems to be making sense to you guys, so we're gonna move on and talk about, I'm just gonna leave my screen on because fairly quickly here, we're gonna use it again. So we talk about oxidation and reduction, what do each of those mean? They give you a couple like, not acronyms, what do you call those? Doesn't matter. A couple ways to remember, mnemonic devices, sorry, to remember those. I think actually it makes sense. So if it does and you remember it that way, great. But if you need something to help you remember it, you can. So oxidation is the process by which an atom loses electrons. And reduction is the process by which an atom gains electrons. So think about it, if something's gaining electrons, do you think that its charge is gonna get higher or lower?
Wait, so which one loses electrons?
An oxidation is losing electrons. Reduction is gaining electrons. But so if something is gaining electrons, do you think its charge is gonna get higher or lower?
It's going to get lower because electrons are negative.
Right, right. So it's getting lower, it's getting reduced. I think it's easy to remember that.
That makes
But if
sense.
it's not, they give a mnemonic device of Leo says grr, like a Leo the lion or something, I guess is how they say it. When lions are angry, they growl. So, but I guess Leo the lion. I don't know. It's kind of a goofy mnemonic device. There was another one I saw too, but it was oil rig. I think that one makes more sense actually than this one. I saw it online. Oil rig. So oxidation is losing, like losing electrons. Reduction is gaining. So oil rig. That makes more sense to me. If you want to use Leo says grr, you can. It's supposed to be loses electrons, oxidation. Grr is supposed to be gains electrons, reduction. Pick whichever thing that makes you remember it and use that. Whatever works for you. I think oil rig makes sense. It's easier to remember, and it like oxidation is losing. Reduction is gaining. To me, it makes more sense, but mnemonic devices don't matter. If they make sense to someone else, whatever makes sense to you is what's going to be useful. So, sorry, I'm so uncomfortable. I'm like sitting on the floor and my feet keep falling asleep here. Okay. So what that means is I look at a charge of something. If I start out with a charge of -2 on some element, and on the other side, when I find its oxidation number on the product side, it's suddenly at 0, would that have been reduced or oxidized, do you think?
Can you say that again?
If it was at -2, and then on the other side in the products, its oxidation number became 0, would that have been reduced or oxidized?
Oxidized.
Yeah, it would have had to lose electrons, right, to get to 0, a less negative charge. Yes, it would have lost electrons, so it would have been oxidation. Versus like, let's say I have something at -2, and then on the other side in the products, it becomes -4. Would that be oxidized or reduced?
Reduced.
Does anybody else agree with that? Emily, do you agree with that?
I don't know what the question was.
If I had a reactant that had an oxidation number of -2, and then when I found its oxidation number on the product side and it became -4, would it have been oxidized or reduced?
Reduced.
Yeah, it was at -2. It had to get 2 more electrons with a negative charge to get to -4. Yeah. So that's the thing that we're going to be evaluating. It really is actually as simple as that. But like anything, when you sort of look at it within an equation, it can feel a little more complicated. So let's look at an example to make sure that it makes sense to us. Let me look at this first example here. These first few examples are basically what I was just saying. Well, we can look at it. A sulfur atom goes from a -2 oxidation number to a +6 oxidation number? Has it been oxidized or reduced? What would you say?
Oxidized.
Yes, it's been oxidized. And it lost how many electrons, do you think?
Oh, wait. It went from -2 to +6?
Yeah,
That means it lost 8.
very good, yes. And you can see the example in the book if it's not obvious to you. You could say -2, how do they do it here? Well, you can just say -2 plus what gives me the 6. It's just, set up as an algebra problem if that's kind of like not intuitively making sense to you. The next one says a carbon atom goes from a -2 oxidation number to a -4, just kind of the one I just gave you. Was it oxidized or reduced? What would you say?
Reduced.
And by how many electrons?
2.
Mm-hmm. Okay, so I think you guys got that part. I want to find one with a, so let's go to example 16.4. So I'm at the bottom of page 567. And they give me a real simple equation here. Calcium plus chlorine gives me CaCl2. And so they asked to find out whether or not it's a redox reaction. That's the short term for that, reduction, oxidation, redox. If it is a redox reaction, identify the atoms whose oxidation numbers changed and tell whether they were oxidized or reduced. So the first thing I have to do is find oxidation numbers. So what is the oxidation number for calcium, do you think? And you can refer back to those rules if you need to. It's rule number 1. I'll give you that clue. You can guess too.
Can you tell me the question again?
You guys have your brains on summer break. I totally get it. Mine is there too. Especially
Wait.
I'm like not even outside with Emily, and I'm distracted by like the nice sounds and outside of that she's experiencing. And I'm like sitting right next to the window. I feel like I'm practically there. So I'm trying to find out what the oxidation number is for calcium. So I refer back to rule number 1, which says when a substance has only
0?
it only has one type of atom. There's no charge on it, so that's 0. Divided by the number of atoms is 1. 0 divided by 1 is 0. So yes, its charge is 0. And the same rule applies for chlorine there. It's one type of atom. The charge is 0. Divided by 2 chlorines is 0. So no charge on that. So 0 plus 0 is 0. That all evens out for that side. But then I have on the other side the same thing. And let's see here. Let me double check something. Make sure I am understanding this properly.
What?
Dasher just ran into my leg with a stick.
When we look at
Like,
that calcium
full force,
chloride,
ran into me.
when we look at that calcium chloride, we can't just take those same oxidation numbers. They don't apply because now calcium is, that rule number 1 only applied when an element, if it was by itself. But now calcium is with something, chlorine is with something. So I'm looking for some rules to tell me about something I might know about each one of those. So I look to see where are they at on the periodic table. Okay, great. Chlorine is easy. It's in that 7A column. I don't know. I don't have any other rules about calcium and about chlorine. So I'm going to go to that rule 7. And so I'm going to see that chlorine has a charge of, or an oxidation number of -1. I'm just getting that from the rule that says if all else fails, go with what it would be if you were trying to find its numbers as an ionic bond. And it's in 7A, so that's going to be -1.
How are you finding the numbers for that ionic bond? Is that just...
You remember when we would go to the column, we had the first 2 over there on the metal side were going to be +1 and +2. And then I could go on the other side, and like if it's in column 7A, that means it had 7 valence electrons, so it's going to be -1. Do you remember doing that?
We wrote the numbers on the periodic table at the top.
Oh, so those.
Yeah.
Like the 1, 2, 3, 4,
Yeah.
-3, -2, -1.
Yes, it comes from that. And so that's where I can see that chlorine is going to be -1. So overall -2. If it's -2, then calcium has to be +2. So now I look and say, okay, calcium went from an oxidation number of 0 to an oxidation number of +2. Did it gain electrons or lose electrons?
It went from 0 to +2. Therefore, it gained, which means it oxidized.
Think about it. If I was at 0 and I gained 2 electrons, I would actually go to -2. But it actually went up to +2. And so it's a little bit in reverse, sort of. It had to actually, or did you say lose electrons? I'm sorry. Did you say lose electrons, Emily? I think I thought you said something else. You said gain? Yeah, it lost electrons, so it became less negative.
Electrons are the negative, so it's losing negative, which makes it more positive.
Yeah. So it increased, I guess you could say, it's positive charge. However you want to think about that, or if it's easier for you to find the one that, because here's the thing, if something's reduced, like if something gains electrons, something else had to have lost or gave it those electrons. So just like a acid-base reaction, it can't happen unless there's an acid and a base. There has to be both. An oxidation-reduction reaction, a redox reaction, is the same way. So if something gets reduced by gaining electrons, something had to have lost those electrons. So if you find it easier to look at the one that, like if you're like, I don't know, 0 to +2, which is that? You could say, okay, but the chlorine went down to -2. It might be easier for you to see that gained electrons. So if it gained electrons, it was reduced. So chlorine is reduced here. And if it's the one that's reduced, then the other one automatically has to be oxidized. So therefore the calcium is oxidized. We'll look at another one of these. So we're looking at the thing that has gained electrons, and so its overall charge is reduced. And then then therefore the other one.
I have to go get him from the chicken coop. I'll be back.
I don't want you to lose any chickens. And then we look for, and then if that's the one that's oxidized, the other one is automatically the one that's reduced. It has lost electrons, and therefore its charge has gotten more positive. So when Emily gets back, we can look at another example. Does that one make a little bit of sense to you? Or no sense at all?
Yes.
That's good. Abby, what do you say? Does it make any sense? Is it? Okay, good. This is about as hard as this chapter gets, really and truly.
Not that bad.
I'll make sure I didn't forget anything, but think yeah, the rest of it is just how batteries work. And to be honest, I would say read that section, because I don't think that I can explain it any better than what they do. And I'm actually going to send you, I was going to just play them, but you can just watch them whenever you want to. Sal Khan has some really nice videos on this too, so if it doesn't make sense in the book, you can watch those if you want to. If it makes sense to you, you certainly don't have to use them. But there's no point in me. I don't think I can explain it better. Oh, how did I just lose both, Katelyn? Did they just disappear? That is so odd. I don't know what happened to Katelyn and Abby. They were like here and they were gone.
Their Wi-Fi probably cut out. It's not the greatest.
Oh, must have. Well, that makes sense if they both left that quickly. We'll see if they make it back in here. And if not, we can do one more and it'll record, and then I'll post that so they can see it. While you were gone, Emily, I was just saying that this is as complicated as this unit gets. Just this, what we just did, trying to see if it was oxidized or reduced. And that's it. That's as hard as it gets. The rest of the chapter is just about how a battery works, how a galvanic battery works. And so what I was just saying is just read that section. I don't think I can explain it any better than what's in there, although if you have questions about it, I certainly can answer them. And I'm going to send you some videos rather than just playing them on here. You can watch them when you want to, from Khan Academy, that explains that too. So if you read it and you totally get it and it makes sense, you don't have to watch the videos, but if it's a little bit confusing, the videos might explain it better. But it's really just the process of seeing how oxidation reduction works in like a galvanic battery, in a car battery.
Yeah, their Wi-Fi did cut them out, she said.
Okay. Oops, that must be them texting me here. Just text them back and let them
You
know.
know, sorry. Dash was trying to, like, apparently dig a hole by the chickens.
That's not good.
I don't know what he's doing.
Well, if you train him not to like play with the chickens and kill them, he might be a good, keep
Well,
vermin away from them.
We're gonna get the chickens out one day, and we're just gonna let them peck him a few times.
Yeah, he's small enough. That'll probably be effective. That's true.
Yeah. As long as the rooster establishes dominance, we should be fine. I mean, like, all it would take is one good spur to poor Dash.
Yes.
for him to be like, oh yeah, I won't touch those.
Sorry, 1 second. I'm like super bad at talking and texting separately. Okay. I'm gonna stop recording and just so they don't have to watch this whole video. Which I think, do I have to stop sharing to do that? No. Stop video for a second. No, that was my video. Stop sharing, sorry.